Okay, and we are recording it. All right, guys. So this is our last lecture in the course, and the topic will be spatial model of segregation. So let's just jump into it and discuss what it is and how it is connected to network science, and look what we can do. So the spatial model of segregation was actually proposed by a Nobel Prize winner now, Thomas Schelling, in 1971. It's one of those of his papers back then, and then it became the basis for a much bigger book by him on micromotives in macro behavior. Actually, hold on a second. It feels like there is an echo. Can you actually hear me well, or there is an echo somewhere?
No, we can hear you.
No, it's okay. It's okay.
We can hear you.
Okay. All right. And the idea of this work is the following. Each of us has some particular personal preferences, but the way we locally interact can create global collective actions, which are not just the sum of our local interactions in some sense, right? So our personal preferences can lead to a very interesting behavior in the society as a whole, right? And the example and the sort of the original work of Thomas Schelling was dedicated to segregation. And segregation can be thought of as segregation by race, ethnicity, segregation by native language, by income. And we all observe, actually, that, for example, big cities are strongly racially segregated, right? And, in spite of the fact that, most of the people, majority of the people are actually quite tolerant to, living among people of different race. And in fact, like sort of America is completely mixed up in terms of the race and ethnicity of the people who live here. But at the same time, we still see a strong expression of segregation in terms of like where people live. And the question that Thomas Schelling wanted to ask is like, well, are the people, racist to that extent that we actually segregating? And so what he found out is that though majority of people have a pretty high, level of tolerance, and in the sense, what I mean by that is that, willing to live with different people surrounding them, and this is a sort of micro preference. On a macroscopic scale, it still leads to segregation, which is actually a very, very surprising result. Now, the model is very simple if we describe it in terms of like every person preferences, but it becomes very complex if we try to model the society in its entirety. And that's why it is a methodology that's been proposed, which is called agent-based simulation or agent-based modeling. In fact, agent-based modeling is quite popular these days. It's used to model and simulate traffic in the city. It used to simulate congestion. It used to simulate crowds. So pretty much those systems where there are agents who can make independent decisions, but we are interested in the behavior of the system in its entirety, in the system as a whole. And we're interested in the dynamics of that system. And so we're going to look into the few simple rules how that simulations can be done, and we'll look at the results, and eventually we'll look onto how network structure affect the results of simulations. Okay, so that's the plan. I'm gonna illustrate this with some simple pictures to like sort of illustrate the terminology and illustrate our points. So first of all, we have two colors. And let's say, we're talking about, actually, we can think about like people living in the city or sort of any other example. But the point, if you have like those two colors, on the left-hand side, you have a very, very good mixture of colors in the sense that, neighboring pixels, they could be green, they could be blue, and it's quite random. And so this is what's called integrated pattern or mixed pattern. And on the right-hand side, you have segregated pattern, where the majority of, well, absolute majority of green pixels are neighbors with green pixels, and blue pixels are neighbors with blue pixels, and only a few, blue pixels have green pixels as neighbors, and other way around. Okay. So on the left side, it's integrated or mixed pattern. On the right side, it's integrated pattern. Okay. So what can we do with this, and how, and what's the story now? Well, let me just give you an example, and this is actually quite telling example of racial segregation in American cities. A bunch of cities: New York, Washington, Chicago, Seattle, LA, Miami, and in every city, it's color coded based on the race of the people who live in the particular neighborhood. And the way to read this color coding is that green is white population, orange is Latinos, gray is black, and I believe this purple is Asian. And for example, if you look at Chicago, you will realize that yes, there is like, say, a lot of white population. Let me change color. A lot of white population living here, right? But then there is like big enclaves of black and Latino population right there. If you look at Miami, you see Latino population living in this sort of two domains, and then there is entirely dominated by black population. Seattle, it's predominantly white, but there is this enclave in the center that is Asian. LA, again, you got this white population here, Beverly Hills and all that stories, and then you get Latinos, and Black LA Central. So, it just, those pictures shows you like very, very significant racial segregation that you observe these days in American cities, right? And it sort of came up, well, naturally, right? Nobody actually placed boundaries, but this is the way, this is the people or agents' preferences in terms of way they would like to live, right? So when a new person comes in, he selects the neighborhood where to live, or when you move in the city, you select neighborhood where to live. And compared to, say, Russia, population in U.S. cities are quite mobile because a lot of people are actually renting instead of just buying homes, and so they actually can relocate quite easily. And they also, buy and own homes a lot. And actually, depending on the job, et cetera, people move. So mobility is actually pretty high. Another example is this one. This is a high school graduates in a Bay Area. So, if you're a little bit familiar with this territory, so this is San Francisco, and right here we got like Stanford and Palo Alto and Google and Facebook. And this area, oops, sorry, and this area is San Jose, and here we got Berkeley. So what you realize again that there, and by the way, up here it's affluent area, up north of San Francisco. So what you realize again, this is high school graduates. The percentile of their young population who are high school graduates versus never finished high school. And you also realize that there is enclaves of the people who never, of students who never actually finished high school. And again, notice that they all live together. They live next to each other. Final example, now it's actually a little bit old example because it's old news. It's from the previous election cycle in the US, but for this cycle, the situation was quite similar. This is political preferences. This is the people who voted for Obama versus back in again 2012 election versus Romney. You realize that again there is a big areas right here along the coast that were Democratic. There is a part here that Democratic, and there is a part up here that is Democratic. There is some scattered Democratic votes in the middle, but then there's a big chunks of red Republican votes. And again, you notice on this picture that color is quite adjacent. One color quite adjacent, red color adjacent to red very often, and blue is adjacent to blue, which shows you very strong segregation in terms of political preferences, right? So of course they're correlated to location, they're correlated to, might correlated to average income, to education, but that tells us that again, in income and education, all those things are also quite segregated, which means people with similar, properties tends to live next to each other, right? And that's yet another example. So the question is, why are we seeing such a strong segregation? Do actually people have such strong preferences? Because if you go like to talk with your friends and talk around, and you think about yourself, you probably don't have that strong preferences in terms of like if you're going to live next to somebody who has the same political opinion as you are, how important is it for you when you're selecting, when you choosing the place where you're going to live. So that was sort of the origin of the questions, right, that were asked, and that's sort of the origin for the Schelling's model. So how it's formulated? Well, the formulation is the following. Let's think about population consisting of two types of agents. And again, to make it very, very simple, right, and we want to make it like simple mathematical, we'll allow agents to reside in the cell of a grid. And we'll be talking about two-dimensional geography. Again, this is a strong simplification, but we need to start somewhere. And in fact, this is think about it, it's more than 40 years ago, right? So pretty much this model was created by pen and paper. So, but the idea is the following. Imagine that we have we have some sort of a grid, and the people can live in different cells of this grid. And you can have two types of agents, and I don't know, I'll have a red agent, right? And let's say, blue agent. And I'll just put them, a few of those. And the idea is that an agent, let's say we're going to focus on this one right now, has neighbors, and overall agent can have like 8 neighbors, and some of those neighborhood spots can be empty. And again, remember, I mean, original Schelling's paper was about racial segregation on where people live. So he was trying to model in some sense like sort of housing situation, right? And you can think about this actually, the houses and the neighborhood, and for Russians this is, think about countryside, dachas. So there is a red agent, and there are people of the same type, and you can think the same type, it can be the same race, the same language, or the same political preferences. And every agent has a preference. He wants to have some of his neighbors of the same type as he is. Okay? And if he does have them of his type, then he's happy. And he just stays there. And if he doesn't, he will move, relocate, and try to find a place where he's happy, where the fraction of the neighbors of his type is as many as he wants. And this process continues with time until we either cannot, there's no place for an agent to move, or everybody's happy, right? So does this make sense? Does this sort of game make sense?
Yeah.
Okay. All right, good. So let's just look at a few details and a few examples, and then we'll just formulate it mathematically. So here's the story. Let's say, the agent, in this case, an agent is the guy with X on it, right? And he's a red guy, and he has preference threshold threshold 3/7, which means he would like 3 out of 7 of his neighbors to be of his type. And what we see here on the left picture, yeah, there were three other agents of his color next to him. So he's a happy or satisfied agent. And on the right side, see here we have only 2 people of his type next to him. And in this case, next means, like horizontal, vertical, and diagonal. And, his threshold is not satisfied, so he's, unhappy, unsatisfied agent. And based on the rules of the game that we're proposing, this agent will be moving somewhere to some other spot where, he will be satisfied with his neighborhood. Okay? And, it's like sort of iteratively all the agents, move. So this is, in fact, right now what we see is a screenshot is a copy of the original images, figures from Schelling paper, where he actually did this drawings with, with a pencil on the paper. And what you see on the left is a sort of original random distribution of people of different preferences. And the empty spots is where nobody lives. And, there are 2 types of people here, right? There is a circle type and there is this type, right? And then after several iterations of this game, where every person or every agent have a chance to move, it actually converges to a situation where you got big islands of people of the same type living next to each other, right? And so that was his, his finding, and he actually did this simulation, by hand. Of course, today, we can do it right on a computer, and here is an example. So what's shown here? Oh, and by the way, so you wouldn't think that this is, the original paper is 1970. People actually still looking at this model a lot, and this is paper of 2009. So what we see here is initial state at time equal to 0. There were, red and blue agents, and vacancy 5%. It means, there's 5% of unfilled sites, so it's pretty dense sort of population. And the tolerance level is 0.5. So it means really that, and I will define tolerance in the next slide precisely, but this means that 50% of the neighborhood can be of a different preference, right? Or not like the person, and person still will be happy. So it's pretty strong tolerance. So he's happy not to move if half of the people surrounding him is not like him. But what you can notice, surprisingly, that in spite of the fact that every person in this game, every agent, is quite tolerant himself. So 50% is a good tolerance level. We still get segregation, and it's forming first into becoming like small islands, and joining, and eventually you get like a complete segregation here. All red agents moving towards with red agents, and all blue agents moving towards the blue agents. And that's actually very, very fundamental sort of discovery. And this is the main point of the work, that though personal preferences might be quite tolerant, it still can lead to a complete segregation for the entire system. That is, something quite unexpected, because you would think that if if each of us are quite tolerant, maybe not 100% tolerant, but quite tolerant, the society will be mixed. But the answer of the model, no, is going to lead to segregation. And that's probably was that's sort of the essence of the paper, and this surprising fact that what made the paper very, very powerful and popular. There are actually more surprises in this story, and these are the simulations with different level of vacancy, right? So you can see like 2, 6, 12, 18%. This is a percentile of like empty spots, and they're like white in this in the white dots in this picture. So you see there are more of them at the bottom than on the top. And what you also see is this, tolerance level, right? And where on the right-hand side we have some on the right side we have a very, very tolerant people situation, quite tolerant, where an agent can have like 3/4 of its neighbors being different from him. And on the left side, we have very, very intolerant people. Now, and that person, that like intolerance here, it means, he cannot take more than one person out of 5 of his neighbors. So like one person out of 5 of his neighbors of different type, that's enough for the person to trigger the move. So what happens is on the right-hand side here, when they're very tolerant, there is they're very, very, very strongly tolerant. Yes, there is a good mixture of the people, and so everybody lives in a mixed state. On the left, everybody is very intolerant, but since there is no enough empty space, they just cannot move. There's no place for them to move. It doesn't matter where they move. They still get a lot of people of different type surrounding them. And so what you have here, this is like on the right-hand side, this is sort of happy society. This is very unhappy, right? Very tense society. But what's surprising that in the middle, where the tolerance level, like 50% or maybe a little bit above, a little bit below, we get a very, very strong segregation. And we get this segregation even if there are quite a lot of empty spots available to move. And so, the idea again of the paper that this is showing why our cities are so segregated. Any questions so far? Okay, I'll move on. So how can we actually make this practical, and how can we use it? And by the way, again, this lecture, has 2 goals. One goal is to introduce you to, the particular model, the particular model of segregation. But the other goal is to actually introduce you to this approach, the agent-based modeling approach, and so that you can actually use it, whenever you want to solve the problems where sort of local moves, you want to solve the problem that affects, that has a lot of number of agents, interacting agents, where the sort of moves for local agents are very simple, but the system in general becomes very complex. So that's the way to solve it. Okay, so just mathematically, this is really, really, really simple. So you have n nodes totally, and let's say theta is a fraction of nodes occupied by both type of agents, A and B. And we're dealing here with 2 classes, but of course, you can expand this theory to include many classes of agents, right? And NA and NB, number of agents of each type. And, again, theta is, it was on the previous slide, it was called rho, it's the same, the percentile, like the filling rate. Actually, you know what? It's 1 minus rho, sorry, because rho was filling rate, and this is a fraction of occupied sites. So then we can introduce the proportion of unlike nearest neighbors. So PI is a proportion of unlike nearest neighbors. So for every node, you just take the nearing, sorry, I'm trying to draw the graph. For every site, you just take and look at the nearest neighbors, and count how many of nearest neighbors are unlike this guy. So if this guy is blue guy, there are 2 red around him, and let's say, let's say there is like 4 blue, but this PI counts number of people not like him, right? So in this case, it's going to be two of them red, and overall there is 1, 2, 3, 4, 5, 6 neighbors. So PI in this case is going to be 2, 6. And then we need to introduce some utility function. So some function that tells you, if the person, if this agent is satisfied or not, happy or unhappy. And this function will have a threshold, tolerance threshold, or, in other words, it's also called sensitivity level. And what it says, if the fraction of foreign type of neighbors, unlike neighbors, is less than threshold for the person, he is a satisfied person. Satisfaction is 1. And if that fraction exceeds the threshold, satisfaction drops to 0. And then mathematically, what we want to do is we want to, every node moves to maximize its utility, because every node wants to be, satisfied. So whenever it's unsatisfied, it moves on. And looking at the entire society, we can look at complete, utility for the entire society, which is the sum of the utilities of the nodes. And we can also look at how mixed the society is. Now, one last thing, important thing, is that so far everything I have described is really based on this idea of cells and people and agents sitting in the cell and looking at the neighborhood. Now, you can actually think about those cells as a graph. But in this case, let's say, to map exactly into Schelling's original problem, this is a node and these are the neighbors, right? So his 8 neighbors. So if we want to mimic or reproduce exactly the idea with cells and neighbors in the cells, then we should have this type of graph as shown on a figure B, where it's square graph but with filled in diagonals. So this is actually exactly the same settings is on the left, but it will allow us later on to put this game on graphs, right? We can just change the the structure, and for every node use the same rules, but now it's going to have not exactly the same 8 number of possible cells next to it, but can have like any number based on the graph structure. So what's the algorithm? And in fact, you can actually just implement this algorithm and see how it works in real life. So you take time steps, and at every time step, you randomly select one agent, in the field, compute the agent utility function, and if utility function is 1, you do nothing with this agent, and if utility function is 0, you move it to an empty location, available location, to maximize utility. Okay? So, one trick here is how to select location you're going to move to, because, if there is enough empty locations, there are a lot of places a person can move. So you can actually, there are 2 sort of standard ways to handle that. You can either move to like entirely a random location, a random location, but still satisfying that utility in that location is equal to 1, and it's empty. So it's empty and utility is equal to 1 in that location. So you can go to random one, or you can say, okay, you know what? Let's actually mimic, a little bit of real life, and we try to, or the agent try to prefer the location that is nearest to the agent, geographically, in the sense of like, if we're talking about graph, is like number of hops from your current location. So select the nearest location that is empty, it's available, and where if the agent moves to that location, it's still it's going to satisfy and give it utility equal to 1. And we're repeating this process. and repeating this process until either all utilities are maximized, and that means, pretty much everybody happy, we have completely happy society, or we reach this frozen state where, there is no place to move. So, every move has been tried and just, no location that satisfies everybody. No configuration that satisfies everybody. And then you can calculate the total utility. So one thing to keep in mind, this is an iterative process, you keep doing until things converge. One thing you should keep in mind that you can, for example, take an agent who is unhappy, move it to another location where the agent is happy, right? But then what might happen is some other agent who is also unhappy, but of different type, moves to the close location to this guy, and some other agent moves to the close location to this guy. And those two red agents might have, good enough tolerance that they get next to this guy. But then on the next step of the game, the blue guy now realizes, oh, he's surrounded again by people of the different type, and then he will have to move again. All right? And so this process continues, it eventually converges, and it either converges to a happy state where everybody is satisfied, or it converges to this frozen state where there is no place to move. Anywhere you move, you're going to be, unsatisfied, and there will sort of percentile of population that remains unsatisfied. And that's like sort of the second part is like, more realistic in real life. But it really depends on the percentile of empty spots available for location. Any questions about this algorithm? Will we be able to implement it if needed? No?
Yes.
Okay. So, like one last question that remains is, we keep talking about this mixing pattern and, population being mixed or segregated. But for an algorithm to give you some sort of results and numbers, we need to define, the level of mixing. Sort of, we need to be able to differentiate numerically the situation where everybody is when everybody is like sort of mixed up and has neighbors of different type versus this sort of segregated story. And there are several indices or metrics you can use to do that. One of them, and sort of the original one, is Schelling's mixing index, which is really just the total number of satisfied, of satisfied customers, of satisfied agents divided by the total number of agents, right? And so if everybody is satisfied, remember this PI corresponds to the fraction of the neighbors that are satisfied. And so this becomes 1 if you're completely satisfied and 0 if not. There's also what's called Freeman segregation index that just calculates the fraction of the edges that goes between similar agents and dissimilar. And edges or ties means they're neighbors to each other. And then there is assortative mixing. If you remember that metric, we talked about it several lectures back. That also actually just counts the number of connections between similar classes, right? So all 3 of those can be used as a measure of sort of mixture within the population. So moving forward, as I said at the beginning of the lecture, the original model proposed by Schelling was on the cell, on a grid with cells. So has been a lot of recent interesting work on taking this model and applying it to network. And the reason for the network type of story is because, again, if you think about like real life, yeah, you don't always have neighbors, surrounding you. There are particular connections. There are like freeways, highways in the city. So there is a much more intricate structure to the neighborhood than just sort of living on a grid. And here is an example where authors took different graphs with fixed number of neighbors. They just said, okay, let's look at the same number of neighbors for every node, but let's look at the different graph types. And let's see if the segregation happens on the graphs depending on like different connectivity pattern in the graph. Remember, if when we talked about, for example, virus and epidemics propagation on the graph pattern, the way things are connected, actually played a significant role in the propagation of infection, how fast it propagates. So the question for the authors was like, okay, we have different type of structure here, underlying structure. How would that structure affect the segregation pattern? Will it still lead to segregation? Or maybe if we have this type of structure, you will not have any segregation, or maybe it enhances it. So here is an answer. And actually, if you look at the paper, you will see more examples. This is an experiment again. The experiment with with a threshold level of 0.5, and with so it's again like 50-50, and with filling of 20%, or theta is 0.8. And so you notice that pretty much left the left one, the left image here, this image, this is really a model for like traditional Schelling's model, right? So this regular grid simulates Schelling's grid cell structure. And yeah, you of course see segregation. Sort of you see a bunch of nodes here, here, here of the same type. Now, if we look at other graphs, you also realize that segregation persists. So it changes a little bit the way things look like based on the structure of the network, but it does persist. So the network structure changes things a little bit, but it does not remove segregation. And sometimes it can actually even enhance it. So I think this is a key slide, for the lecture, and a key slide for those findings for the papers. So on the horizontal axis, we have a tolerance level. Again, how tolerant people are. And on the vertical axis, we have mixity, or level of how mixed up the population is. And so what you see here is that on the very right, when people are tolerant, like very, very tolerant, so they don't really, they don't really care who are the neighbors. Of course, everything is mixed up, right? It starts with random state, it stays in random state, and then you can look at this as grid, which actually original Schelling experiment. This is a random network, scale-free network, and this is what's called fractal network. They wanted to also look at the fractals, which is the network that has this very strong self-like hierarchical structure. So you notice that the situation is sort of obvious, and there is no really difference. Now, when we are right here, so this is very tolerant. On the left side, we have completely intolerant society, where everybody doesn't want to be next to anybody except of people like that person, but because there's not enough space to move, they are it's again mixed. It's just there is no way out. And so in some sense, this is like very positive society, right? And this is actually quite negative society. Everybody's unhappy. But what's interesting is that, again, in the middle, where people, like 50%, again, where people are willing to have half, or actually even more than half of their neighbors, like 60%, or even like here 70% of their neighbors of a different type, there is still segregation occurs. So mixity here is very low. And that means, you know, there is a strong segregation. And notice that for this fractal system, and by the way, fractal again, one more time, so you would know what it, remember what it is. It's this is a fractal, right? This is sort of structure, similar structures. So for the fractal, we get the strongest segregation pattern. And random also kind of enhances segregation. Look, if you compare random, the green is below regular. So, you know, sort of random network actually, and scale-free network, all of them enhancing segregation. So in this sense, a regular grid is in some sense, you know, the layout where you will have the least segregation and the best sort of possible mix. Again, you know, take this with a grain of salt because this is the model. But you know what it shows, what it tells you is, first of all, that yes, there is a sort of part of the parameter space that tells you that yes, people are tolerant as individuals, quite tolerant. But when they act together as a group based on sort of individual preferences, the general group dynamics leads to segregation. And second is that yes, network structure does affect segregation, and you know, the less connectivity you get within the network, the worse, you know, segregation will become. And so this is something that actually should be taken into account when people design cities. It's not, but it should. So I guess a summary for the lecture that the spatial segregation is taking place even though no individual agent is actually seeking it. No individual agent is racist, but even the small intolerance, it leads for the group to segregation. And network structure does affect segregation. And as a result, those sort of fixed characteristics of the people, like, you know, like race or you know, ethnicity, becomes correlated with mutable characteristics like location, and that instantly affects things like, you know, like income, like election results, etc., etc., etc. So that's pretty much it for the model. Any questions?
What's the difference between segregation and classification?
Say it again. What's the difference between segregation and
Classification.
Well, the question was about difference between segregation and clustering.
Oh, segregation and clustering. Yeah, so when we're talking about clusters, this is about network properties, right? So this is only about the network. It's about the network structure, right? So if you have, you know, groups of nodes that are tightly connected, you know, that's the forms that's the clusters. Now, segregation, it's an agents that act on top of the network, right? And you know, you might have clusters, but it might happen that within the cluster you will get, you know, mixture of different types of A and B agents. But I agree that when you see clusters, more likely because of those cluster boundaries, you will get, you know, segregated group or group of the same type of people within each cluster. That, you know, that will definitely affect it. But again, clusters, it's about the network structure. The segregation is about agents acting on top of the structure. Does it make sense? All right, guys. So yeah, and there are references for those of you who want to look into this. I guess, you know, that's pretty much it with our short course. This is what we have done, right? I mean, it was just 9 lectures, but we actually managed to cover a lot. So we talked about introduction to network science. We talked about what network science is. We discussed various ways to, you know, analyze networks, and we talked about, statistical properties of the networks, things like density, number of edges, the shortest path in the network, clustering. Then we talked about mathematical models of networks, and we discussed several theoretical models of how networks form, including random networks and preferential attachment. Then we discussed things like the importance of the nodes within the network, which is network centrality, node centrality, and the ways to rank nodes on the networks. We then looked into clustering and talked about network communities and how to detect them. And pretty much all these lectures, I should say, put it this way, these were about describing network structure. And then we moved on to, actually, there's another one, network structure and visualization. I missed that one. It was about, network and a connectivity pattern and overall network structure, and how to present it, how to analyze it, how to understand it. And then we had 3 more lectures on the processes. So this is structure, and this is process. So on the processes happening on the networks, and we talked about spread of epidemics, like flu or viruses, or information on that substrate of the network. And the substrate here is usually will be like either friendship graph or maybe traveling patterns. We talked about diffusion of innovation, or a model of making decision when you are actually surrounded by friends, and they affect your decision because they influence you, and because you're as a rational agent making a decision that optimizes your preferences, like either joining the same mobile operator or switching to a new technology, and your decisions are based on what your neighbors do, friends do. And finally, today we talked about the spatial model of segregation, where again on the agent-based sort of level, we realized that though there are certain microscopic properties and actions can give to very interesting macroscopic behavior of the entire system. So this goes from, like, again, microscopic to macroscopic. So that's pretty much it. That concludes the course, and you will have one more today, one more lab seminar, and then you'll have a final. Questions? Concerns? Complaints? Comments? Okay. I think everybody is ready for the summer. Yeah, Andrej.
Yeah. So we will start classes in 5 minutes.
Okay. All right, guys. Well, thank you very much.
Thank you.
It was good working with you.
Yeah.
Enjoy the rest.
Okay, so we'll connect to another Zoom in 5 minutes.